This experiment is a super fun one. We're going to be making ice cream. So first we're going to go over the materials we need to do this experiment, then we'll get right into it. So making ice cream surprisingly only requires some simple materials. So what you need to make ice cream is 1 teaspoon of vanilla extract, 1 quart-sized bag, 1 gallon of ice cubes, 2 gallon bags, 4 tablespoons of granulated sugar, a half pound of iodized salt, but this doesn't have to be perfect. You don't need exactly half a pound, and 1 cup of milk. Whole milk works the best, but if you have any other types of milk, that's fine too. If you want to use a dairy substitute, coconut milk might also work. I didn't really test it out, but I've seen that could also work. So the first thing you're going to do is take your quart-sized bag and pour in the milk. The next step is to take a teaspoon of vanilla extract and pour it inside the quart-sized bag with the milk. The next step is to take the 4 tablespoons of granulated sugar and put that in. After that, close up the bag and set it aside for now. Next, take your 2 gallon bags and put one inside of the other. Then pour the ice into the 2 gallon bags. Next, take the half a pound of iodized salt and pour it into the ice. This is the main scientific component of this experiment, which we'll talk about later. Next, take the quart-sized bag and mix up all the ingredients inside. Then seal the bag up and put it inside the 2 gallon sized bag with the ice inside it. Make sure all the bags are sealed super tightly so that nothing leaks and that the salt water does not get inside the milk mixture. Otherwise, you'll get really salty ice cream, so that isn't good. After everything is sealed, shake the bag for 10 to 15 minutes. Put on gloves after a while because the ice will get super cold. Once everything's done, you can slowly open everything up and take the ice cream out. Rinse the bag before you open the ice cream mixture so that the ice doesn't get inside the ice cream, and then enjoy. So now let's talk about how this works. When you add the iodized salt to the water, the freezing point of the water-salt mixture is now much lower than it was before you added the salt. So you might see that when it snows outside, people might add salt to their driveways in order to melt the snow and clear up the driveway. The reason for doing this is very similar to what we're talking about now. If you add the salt to the water, the freezing point is much lower, which makes this mixture melt faster because it is nowhere near to its freezing point. However, in order for it to melt, it needs to take heat from an outside environment. In this case, it takes the heat from the milk mixture we made earlier. As we mentioned, when things melt, they absorb heat from their outside environment, which makes the outside environment become colder. In this case, the water and salt mixture absorbs a lot of heat, which makes the outside surroundings turn very, very cold. This allows the ice cream mixture to become cold enough to harden and combine and turn into ice cream. So that's how this works. It's super cool and so tasty. So I hope you guys all enjoyed this video. It was super fun to make, and I hope that you guys have an equal amount of fun doing the experiment. And I'll see you in the next experiment where we play around with density to make an egg float. In this experiment, we're going to be making an egg float. All you need to do this experiment is a glass cup, water, an egg, some salt, and a spoon. Our first step is to lower an egg into a glass cup filled with water. Observe what happens. We can see that the egg totally sinks to the bottom of the cup. Then remove it and add some salt to your water. After you've added some salt, mix it until it is completely dissolved. Now that all the salt has dissolved, we're going to take our egg and place it back in. We are testing to see if it floats or if it still sinks. If it still sinks to the bottom, add more salt and stir it until it is completely dissolved and keep testing it. Repeat this process until your egg floats into your glass. Once you've gotten your egg to float, take some more water and pour it until it reaches the very top. And you can see that your egg floats right in the middle of your glass. Now let's discuss the explanation for this experiment. The main theme, or the main scientific topic that we're looking at here, is density. Density is defined as the amount of grams per cubic centimeter in a substance. So grams refers to mass. We're looking at the amount of stuff, to put it quite literally, in a cubic centimeter, which refers to volume. Volume is the amount of space that something takes. If you were to take 2 boxes of the same size and put 2 books in one of them, and then fill the other one with 10 books, then we would say that the one with 10 books has more density, or it is more concentrated because it has more stuff in the same amount of volume. And we're doing the same thing here, except we're looking at it in a very, very small, microscopic way in which we can't see with our bare eyes. So if we look at this diagram on the left, we can see a relative density of the 2 substances that we are observing. In each box that I've placed, there are many, many, many molecules, but I've only shown a few so we can get a basic idea and compare the relative densities. When we talk about density and water, we're often referring to if things float or sink. If something is more dense than water, then it will sink, and if it is less dense, then it'll float. So from this, we can tell that the egg is more dense than the water. In the relative densities that I've shown, I've put 2 dots in the water and 3 dots in the egg where these boxes of the same size are shown. And this is just to show that the egg is more dense, not an exact ratio. Then on the right, we can see the salt water and the egg is now floating. We can see that there are more particles in the box with the salt water compared to the box with the egg. And this is because we added salt, which makes there be more stuff in a given volume. Now let's look at the diagram when we added more water. Now the egg is floating right smack in the center of the glass. And this is because the salt water is at the bottom and the plain water is at the top. The salt water is more dense, and therefore not much mixing occurs between the salt water and the pure water. So the pure water is less dense and stays at the top of the egg, and the salt water is more dense and stays at the bottom, leaving the egg to float right in the center. That concludes this experiment. I hope you now have a good grasp on what density is. And I'll see you in the next experiment, in which we look at another application of density and another super fun way of learning science. This experiment is called Dancing Raisins. This one is a super fun one. Let's get right into it. For this experiment, you need Sprite or any other carbonated drink and raisins. The first step for this experiment is to drop your raisins into your carbonated drink. Now simply observe what happens. As you can see, the raisins first sink into the carbonated drink, and then they rise up and then sink again, and it's a cycle that just keeps going. So now let's start talking about how this experiment works. So the raisins first sink to the bottom of the glass because the raisins are more dense than the carbonated drink. If you were to take 1 unit of the raisin and the same unit of the carbonated drink, that means that there will be more in that unit, it'll be more compacted. The molecules, what's in the drink and the raisins, there'll be more of it in the raisins than there will be in the carbonated drink. So that's a super simplified explanation of density. The soda releases carbon dioxide bubbles, which attaches to these raisins and acts like a little flotation device, bringing the raisins to the top of the surface. Since the carbon dioxide bubbles are less dense than the soda. When the carbon dioxide bubbles attached to the raisin reaches the top, the bubbles pop and the raisins go back down to the bottom. When the soda is flat, which means that it's no longer releasing carbon dioxide, this process stops. So that's how this experiment works. And that concludes this experiment. I hope you enjoyed it, and I'll see you in the next experiment where we look at a twist on the classic lava lamp experiment. In this experiment, we're going to be making a lava lamp. We are going to make it glow using a blacklight and quinine water, but if you don't have these things, don't worry, you can just make a normal lava lamp. For this experiment, you will need a glass jar filled with oil and Alka-Seltzer. Those are the necessary materials. If you want to make it glow in the dark, you need a black light and tonic water that has quinine. The first thing you need to do is put your water or quinine water into the oil jar. If you just have water, you can also add food coloring. If you have quinine water, don't. And so the next thing we're going to do is find a room with no windows that's absolutely dark, and then we're going to turn on the black light. You can see that on the left I have just water, and on the right I have quinine water, so you can see the difference between the two. Now this is where the fun comes in. Drop the Alka-Seltzer into the jar and you can see a lava lamp-like effect. It's super cool, and you can watch it all day. You can just keep adding Alka-Seltzer to continue the reaction. If you would like to just do a normal lava lamp, it'll also have a similar effect. So now let's talk about how this experiment works. Let's first talk about how quinine water glows when exposed to UV lights. So the reason for this is that quinine has a compound called phosphors in it. And phosphors are able to absorb UV light and emit it again as this greenish blue color. So that's what's happening in this situation. The phosphors in the quinine water are absorbing the UV light from the black light and then emitting light in this color that we see. Now, how does the lava lamp-like effect occur? Well, the reason why the water sinks to the bottom when you add it to the oil is because it is more dense than oil, and they don't mix because they both are what scientists call immiscible liquids, which means that they don't mix together. The reason for this is that water is what you call a polar substance and oil is what you call a non-polar substance. So because they're not the same, they don't mix. When you add Alka-Seltzer to the jar, it reacts with the water to create carbon dioxide. The carbon dioxide sticks to the water and rises to the top of the jar. There, the carbon dioxide bubbles pop and it returns back to the bottom of the jar. And it keeps doing that over and over again until the Alka-Seltzer and water reaction stops. So then when you add more Alka-Seltzer, it keeps going on. A similar process occurs in one of our previous videos called Dancing Raisins. And that concludes this experiment. I hope you enjoyed it, and I'll see you in our next experiment. Welcome to our next experiment. This one is called the Levitating Match. We will be dealing with fire, so make sure to have an adult with you at all times. Now let's jump right into it. For this experiment, you need either a small cardboard box, or if you don't have one, you can follow along with the other option that we're going to use in today's video. For the alternate option, you need some tape, scissors, and a piece of construction paper cut in a square. And regardless of the option you use, you need 3 matches or 2 matches and a lighter. To begin with, if you don't have the cardboard box, take the black piece of paper and fold it as shown in the video. After you've folded it, cut the 4 tiny squares that you've made in the corners. After all the squares are cut, take some tape and connect each of the 2 sides of the square that you cut out together. Now you've made a box. Take a safety pin and poke a little hole right in the middle of the box. If you have a cardboard box, then do the same thing, and after you've poked a hole with a safety pin, put the match inside the hole. Take another match and lead it across the side so that the 2 heads are connecting. Then take your lighter or match and light right in the center of the leaning match. Once it catches on fire, you can take the lighter or match away and watch what happens. Please make sure that an adult is the one lighting the fire for you and that you are not doing it yourself. How it works is that when you light up the center of the leaning match, the bottom of the match is quickly burned. Because of this, the weight of the match becomes minimal. After the fire spreads to both of the heads of the matches fuse together because both of the heads have lit up, and because the weight of the leaning match has become so light, it rises and looks as though it is levitating. So that concludes today's experiment. I hope you enjoyed it. I certainly did. And I'll see you in the next experiment, where we look at a gravity-defying application of air pressure. In this experiment, we're going to be looking at a pretty common trick and learning the science behind it. Let's get right into it. For this experiment, you're going to need a bowl, an index card or playing card, a piece of paper that's thick enough and also large enough to cover whatever cup you're going to use that's filled almost to the top with water. Those are the only 3 materials that you need. To begin, take the cup filled with water and place the index card on top. Secure your hand over the top of the index card and slowly flip it over. It's natural for some water to spill out while this is happening. Then, gently let go of the bottom of the card. It's floating! The water is staying inside and the index card is not falling out. This is truly amazing science, and we're going to discuss why this happens and how in the world it's possible. The basic idea behind this experiment is air pressure. Let's think step by step about what happens to the cup and outside of the cup when you do this experiment. Initially, when you have the water and a little bit of air at the top of the cup, the inside and the outside of the cup are equal in air pressure. You cover the cup with the index card and you flip it over. Now, some of the water, when doing so, comes out of the cup. When some of the water comes out, the amount of air is the same inside the cup. However, now that air is occupying more space than it was before, because now that there's less water, there's more space for the air to occupy. And now because the air is more spread out, it's going to exert less air pressure than it did before. When this happens, and when it's exerting less air pressure, the outside is going to have more air pressure than the inside. Because the outside air is exerting more air pressure, the card will stay in place, and thus creates this airtight seal that causes this super cool experiment. Welcome to our day 7 experiment. Today we're going to be doing an experiment called the copper-plated coin. This experiment requires a little more advanced material, so if you don't have everything, that's totally okay. Just watch the video and enjoy the super cool science. Let's get right into it. For this experiment, you will need vinegar, rubbing alcohol, a plastic cup, a 9-volt battery, a Sharpie, 2 copper electrodes or copper strips, a quarter or nickel, a 9-volt battery snap and alligator clips, and a paper towel. The first thing you need to do is take your marker and mark a plus and minus signs on either side of your plastic cup. Then pour vinegar around 2 inches into the plastic cup. Next, attach your 9-volt battery snap to your alligator clips. Since mine are already connected, I do not have to do this. Then I connected the snap to the 9-volt battery. After this, I connected each alligator clip to the copper strips. Take each copper strip and carefully place them in the vinegar. Make sure that the red is at the plus sign and the black is at the minus sign. Your setup should look like this. Wait until the vinegar turns blue as shown in the video. After this has happened, you can take your quarter or nickel and clean it with rubbing alcohol. After you have cleaned the quarter, do not touch it. Use something else to carry it. Next, remove the copper strip from the negative side of your setup. This one should be the black alligator clip. Then attach the quarter to that black alligator clip. Slowly lower the quarter into the setup and tape the setup so that the alligator clip is not touching the vinegar, only the quarter is. After you've completed this setup, you should leave it for around 30 minutes to 3 hours. It ranges depending on your materials. For us, it took almost 2 to 3 hours for this experiment to work. After waiting, take the tape off and take the quarter out of the setup. A copper black substance should have formed over your quarter. Remove the quarter from the alligator clip and clean it off with a paper towel. As you can see, a copper layer formed over the quarter. You can see that the place where the alligator clip, it's more silvery than the rest of the quarter, and this shows that a copper layer formed over the quarter. So now let's talk about how this happens. In the first step of this experiment, we did something called electrolysis. As you can see in the picture, in one of the copper strips, some of the copper almost came off of the copper strip, and on the other one, some of the copper layered on top of it. From this, we can see that in this setup, some copper left one of the strips and transferred onto the other strip. This is because in this setup, the vinegar is causing this reaction and electricity to flow in this circuit. The battery is powering this reaction. Little bits of the copper removes from the positive side of the setup, which was the red alligator clip. It comes off of that copper strip, goes into the vinegar, and we can see that there's little pieces of vinegar little pieces of copper that's in the vinegar later. And some of the copper layers onto the other copper strip. In a similar way, when we add the quarter, the copper is collecting onto the quarter and is plating it. So that's why the second step is called electroplating. Well, why does the vinegar turn blue? This is because not only do small bits of copper collect on the bottom of your cup in the vinegar, but it also reacts with the vinegar and it turns blue. one of the indicators of a chemical reaction, so basically one of the things that show that a chemical reaction has occurred, is a change of color. So the vinegar and the copper have created this chemical reaction and turned blue. Thank you all so much for watching this video. I really hope you enjoyed it and learned something from it, and I will see you next time. Hi everyone! Today's experiment is going to be a little different. We're going to be doing some science, but also some art at the end of it, having fun with our creation. So let's get started. For this experiment, all you need is a cup of milk, 4 teaspoons of vinegar, and a strainer. You're going to also have to boil the milk on the stove, just a little heads up. And now let's dive into the experiment. So the first thing you have to do is boil the cup of milk on the stove until the milk is warm but not boiling. Pour the milk into a separate bowl. Then pour the vinegar inside the milk. Then stir it until a clumpy mass starts to form inside the mixture. Yours might come out a little more scattered and not all clumped up together. It varies for like the type of milk that you use. Whole milk is better. And then after that, you can play with the new plastic, I guess, that you just formed, and make whatever you want. And after, you can decorate it, paint it, do whatever you want with it. If you leave your creation out for like a day or two, it'll start to harden and your creation will become plastic. We did a little decoration with ours to make it look like our Powerlin logo. You can do whatever you want with your plastic milk. And now we're going to talk a little bit about how this experiment works. When you add vinegar to the milk, the acidity of the milk changes. It becomes more acidic. There's a substance in the milk called casein, which is Latin for cheese. The change in acidity causes the casein in the milk to unfold and separate from the rest of the milk. The casein does not mix well with the vinegar and separates itself into the blobs that we see. That concludes today's video. I hope you enjoyed it, and I'll see you next time. Hi everyone! In this video, we will be doing an experiment to visualize how a tornado is formed and how it works, and learn more about tornadoes in general. So, let's get started. For this experiment, you need a jar filled with water with a little bit of space at the top, around 1 inch, and some hand sanitizer. If you do not want to use hand sanitizer, you can also use a teaspoon of vinegar and a teaspoon of dishwashing liquid mixed together as a replacement. Open the lid and place 2 squirts of hand sanitizer inside the jar. If you are using the replacement, place your mixture inside the jar. Place the lid back on the jar and spin it around in a circular motion as shown. Place it down and you should see your tornado inside of the jar. So now let's talk about how this works. In the center of the tornado, we can see a small amount of space in which not much is occurring. The circling water is spinning around the center of the tornado. The center is called the vortex, which is commonly known as the eye of the tornado. We typically hear that the eye of the tornado is the calmest part of the entire tornado. The reason for this is that all the motion is occurring around this fixed point. The water that is spinning around the vortex is spinning due to centripetal force. Centripetal force is a force that causes an object or fluid like water and air to move in a circular motion directed by its center. In this demonstration, we used the fluid water to demonstrate a tornado. In a real tornado, air is what will be spinning around and causing a tornado instead of water like our demonstration. The hand sanitizer or dish soap and vinegar is there so that we can see the tornado clearly. So that's how a tornado works. So that concludes today's experiment. I hope you enjoyed it, and I'll see you next time. Hi everyone! In this video, we will be doing an experiment demonstrating how clouds are formed. You will only need a few simple materials to do this experiment. So, let's get started. For this experiment, you need a bottle of hairspray, a jar with a little bit of water, and some ice on the cap of the jar. And you might also want to use a black piece of paper. First, heat up the jar in a microwave for around a minute. Use oven mitts and place it down. Immediately put the cap with the ice on top to trap the steam inside. After leaving the cap on for some time, spray some hairspray inside of the jar and immediately cover it again. Leave it there for a little bit and wait for the inside of the jar to fog up a little bit. As shown, you should start seeing a cloud-like fog build up inside of the jar. After waiting for a few minutes, lift the cap off and see the cloud-like fog come out of the jar. The black paper is placed behind it so you can see it better. So now let's talk about how this experiment works and how clouds are formed. When you heat the jar with water, the water turns into water vapor, which is a gas form of water. This water vapor travels to the top of the jar and cools because of the ice at the top of the jar. The ice causes the water vapor to condense into water. Condensation is when a gas cools into its liquid form. The condensed water then needs something to cling onto in order for us to be able to see it. In this case, the hairspray is what the condensed water clung onto. In the real world, when water evaporates into water vapor, the water vapor clings on to dust particles, air pollution, or pollen in order to be visible. So that's how a cloud is formed. The water cycle is the process by which the water gets from the land to the air and vice versa. In this simple diagram, we can see the basic components of the water cycle. So first, pause this video and try to figure out if you can determine what 1, 2, 3, and 4 represent. And then play the video again and see if you're correct. So now let's talk about what each of these arrows and numbers symbolize. 1 is representing the heat that the sun gives off. 2 represents evaporation. Evaporation is the process by which water turns into water vapor. The arrow from 1 is pointing towards 2 because the heat from the sun is what causes evaporation to occur. The water vapor then condenses or turns from its gaseous state to its liquid state, and in 3 becomes a cloud. The condensed water clings on to dust particles or air pollution or pollen, as we mentioned previously, and turns into a cloud. When the cloud no longer can bear the weight of the water, it precipitates, which is represented by arrow 4. So this is the process of the water cycle. So that concludes today's experiment. I hope you enjoyed it, and I'll see you next time. Hi everyone! In this video, we will be doing a magic-like experiment in which we demonstrate potential and kinetic energy in action. So now, let's get started. For this experiment, you will need some tape, 2 paper clips, a rubber band, a 9-volt battery or a similar weight and size, and a can. I use a Pringles can, but a larger can would actually work better for this experiment. But if you have a similar size one, that's fine. And then poke a hole with a screwdriver on both sides of the can. Ask a parent to do this for you. It's a bit dangerous. So first, take your 9-volt battery or similar weight and place the rubber band on both sides and secure the tape over it as shown in the video. Take the apparatus that you just created and place it in one of the holes in the can. It's better to start with the one on the bottom. Pull the rubber band through the hole and take your paper clip once you've done so. Place the paper clip inside the rubber band without securing any parts of the paper clip inside the band. And then do the same thing through the lid of the can and secure it with the paper clip on that side as well. Once you finish, it's time to test your device. Take the can and place it on a surface. Roll it and see what happens. If your can is not rolling back, as shown in the video, don't worry. Another way to see the energy in motion is to spin it around and place it on a surface. It should roll as shown in the video. So now let's talk about how this experiment works. When you roll the can, this is kinetic energy. The can is in motion. While you are doing this, inside the can, the rubber band is twisting as shown in the picture. This twisting has potential energy stored inside it. Once the can stops moving to one side, this potential energy turns into kinetic energy and starts unraveling, and the can starts moving to the other side. In our troubleshoot option, if your can was not rolling back to you, we spun the can ourselves and then placed it down. In this situation, you are causing the kinetic energy and creating the potential energy to build up inside it. And when you place it down, the potential energy that's stored in the twisting of the rubber band is released and the can moves. Pretty cool, isn't it? So that concludes today's experiment. I hope you enjoyed it, and I'll see you next time. Today's experiment is called Exploding Baggie. It's a twist on the classic baking soda and vinegar experiment. Very simple and only needs a few materials. So now, let's get started. So for this experiment, the first thing you're going to do is take a plastic baggie and put in a half cup of vinegar and a 1/4 cup of water as shown on the plastic bag. And then take 3 tablespoons of baking soda and put it on a piece of tissue. Then fold it as shown. After you're done folding the piece of tissue, either go outside or place a tray underneath your experiment, and then lower that piece of tissue with the baking soda into the baggie and quickly close it. Then just step back and watch what happens. You should see that the piece of paper is slowly inflating, but if it's happening very slowly, you can pick up the bag and shake it a little bit so the baking soda goes into your mixture. And then place it down again and watch, and don't be startled. The Baggie should erupt as shown. And after this happens, the experiment's done. Now let's talk about how this happens. So as we've talked about in previous experiments, baking soda is a base and vinegar is an acid. And when you combine a base and an acid, a base-acid reaction occurs, a chemical reaction. So in this case, when vinegar and baking soda are put together, carbon dioxide is formed, and this carbon dioxide keeps filling the bag until finally the Baggie explodes. So that's basically what happens in this experiment. So that concludes today's experiment. Thanks for watching, and see you next time. Today's experiment is called M&M Experiment. Let's get started. All you need for this experiment is a plate, some Skittles or M&Ms, and some warm water. After you arrange your M&Ms or Skittles in the circular pattern shown, pour some warm water into the middle of the little circle that you created. Pour it until the M&Ms or Skittles are covered completely, and then observe. So now let's talk about the science behind this experiment. So first things first, the M&Ms or Skittles, the color dissolves because the sugar in these candies are easily dissolvable. So that's why the colors, you can see the colors after you put it in water for a while, and we use warm water because things dissolve easier in warm water. So that's why that happens. Now let's talk about why the different colors don't mix. The reason for this is that the concentrations of each of the colors are pretty similar, so they don't really find a need to mix together. In other words, if there is a gradient or a difference between concentrations, then each of the colors are going to mix to try to even that out, because nature is always looking for equilibrium or balance. Another example of this that you might be familiar with is if you put an ice cube in your hand, then that ice cube will melt. And the reason for that is that there is a difference in temperatures. So the coldness of the ice cube is going to transfer into your hand, and the warmth will transfer into the ice cube until your hand and the former ice cube will be the same temperatures. And this is again to find equilibrium or balance between the two. So hopefully that helps you envision why the colors don't mix in this case. Because there's no gradient or difference between the concentrations, there's no need to mix. So that concludes today's experiment. Thanks for watching, and see you next time. Today's experiment is part 2 of the experiment we did yesterday. The similarity between the two is, you guessed it, they both use M&Ms. All you need for today's experiment is a bowl that is deeper than the one you used yesterday, some room temperature water, and 4 M&Ms. So let's get right into it. The first thing you need to do is take your M&Ms and place them in a sort of circular pattern inside your bowl. And then pour in some room temperature water so that the M&Ms are covered and more. So if you have like a short bowl like we do, just fill it up completely. And you don't necessarily have to straighten out your M&Ms back into the circle if they move around, but if you want to, you can, so that you can see better results. And then after you do that, you just have to wait and observe what the M&Ms are doing. After a while, you should see that the M's on the top of the M&Ms float off. So that's what we'll be seeing in a little. Now our clip is back to normal speed because we can see that the top of the orange M&M is starting to peel off. So we're gonna have to wait a few more seconds. And now the top of that is floating to the surface. So as you'll now see, the M of the M&M and a little layer on top has floated to the top of the water, as you can see. The top of the coating of the yellow M&M has now floated to the surface. So we'll see that now too. And now there's a clear view of the M. So now we're going to wait a little more for the brown M&M. And now the top of the brown M&M is floating to the top of the water. Floating, you can see the complete M. When we picked it up, unfortunately, this one broke apart. So the blue M&M was quite stubborn. It took almost 20 minutes for it to come up to the top. So we stopped the video, and finally it did come up, but the M broke apart before we could see it. So this is what the blue M&M looked like after 20 minutes, and you can see that the M isn't visible. So now we're going to talk about how this experiment works. So as we talked about in the last video, which if you haven't watched yet, you should, the coating of the M&M is made out of colored sugar. So this sugar is easily dissolvable in water. So once you put water in it, the sugar just dissolves right off. The difference with the M's, though, is that the M's aren't made of just sugar. So because of this, they take longer to dissolve in the water, and they obviously, because they're less dense than water, once the sugar comes off, there's nothing to stick to the chocolate of the M&M, and it just floats right up to the top of the water. So that's how this experiment works. So that concludes today's experiment. Thanks for watching, and see you next time. Welcome to our Day 15 experiment, Dry Erase Magic. I'm sure you're going to have a lot of fun with this one. Let's dive right into it. All you need for this experiment is a glass surface. It can be a tray or a plate, and a dry erase marker. With the dry erase marker, just draw a simple figure on your glass surface. And you also need some water in another cup to pour into this tray later. So the first thing that you're going to do for this experiment is to pour water on the bottom of the tray. And then after you've poured water, slowly, that's very important, do it very slowly, just tilt the water into your figure, and you should see that the figure starts to come off the surface of the glass. And soon it'll be away from the glass and you can start playing with it. It's like magic. How this experiment works is very simple. The material that the dry erase marker is made up of is not soluble in water, meaning it does not dissolve in it. Therefore, when water comes underneath it, it does not suddenly just disperse into the water. Also, the dry erase marker is less dense than water, so when you put water underneath it, it's going to try to lift above the water. So because of a combination of both of these things, the stick figure, when you put water underneath it, it lifts off the surface of the glass because the glass is a very slippery and frictionless surface, so it easily lifts off it. That's why we use glass specifically. So when the water goes underneath it, the solid dry erase marker, it lifts off the glass, trying to get above the water, and that's how our stick figure made up of dry erase marker is able to lift off the surface of the glass and float around. So that concludes today's experiment. I hope you enjoyed it, and I'll see you next time. Hi everyone, and welcome to our Day 16 experiment. Through this simple activity, we're going to be looking at how differences in temperature affect the speed of molecules. So let's get right into it. For this experiment, you need food coloring and 3 clear jars. You need to put water in all 3 clear jars, leave one at room temperature, keep one in the freezer for a little bit until it is 40 degrees, and the other one heat it up until it is around 100 to 130 degrees. So once you do that, just put food coloring in all 3 and observe. So now let's talk about the differences that we see and why we see them. The one all the way to the left is the one that's the coldest, the one in the middle is room temperature, and the one all the way to the right is the warmest one. So molecules move really fast at hot temperatures, stay at a steady pace at room temperature, and move really slowly in cold temperatures. So that's why we see the differences between these 3. You can see that the food coloring is moving much slower in the colder water than it is in the others. The hot water, immediately the food coloring just spread everywhere really fast and then completely combined. The room temperature one is kind of moving steadily. It's not really going at too slow or too fast, and so that really demonstrates the differences of the speeds of the molecules in these 3 different temperatures. So that concludes today's experiment. I hope you enjoyed it, and I'll see you next time. Today we're going to be doing an acid-base reaction. So it's not going to be the classic baking soda vinegar experiments that we always see, so it'll be a fun twist. Let's get right into it. So you're probably used to the classic vinegar and baking soda experiment, where you take some baking soda, you put in some vinegar, and then you see an explosion. The reason for such a reaction is because vinegar is an acid and baking soda is a base. And so in this experiment, we're going to be taking the acid lemon and we're going to be mixing it with baking soda and see what happens. So for the experiment, you need a glass cup, and in the glass cup, put in 1 tablespoon of baking soda and 1 teaspoon of laundry detergent, and put that in a larger tray so that you don't spill anything. And you need lemon juice. For that, all you need to do is squeeze some lemons into another cup and you're all set. So all you need to do for the experiment is just to pour the lemon into your laundry detergent and your baking soda mix, and you'll see that it immediately foams up. So it's very similar to what happens when we put baking soda with vinegar. So you can see that the similarity between the two is that it's an acid and base reaction. And so the only difference here is what the type of acid is. In a close-up view, you can see how much it foamed because of this reaction. So now let's talk about how this happens. So first off, acids and bases and pHs are a very deep topic to be discussed. So I'm not going to go too deep into it, but I'll cover some of the basics that you need to know. We'll be going further into pH in the last experiment of this video, so don't worry too much if you don't understand what I say for now. So first things first, pH stands for power of hydrogen, and it basically measures the concentration of hydrogen ions in the substance. So again, we're going to go further into this at the end, but acids basically have more hydrogen ions and bases have less of them. And bases instead have something called hydroxide ions. So the main thing for you to know is that lemon juice and vinegar both have a pH of 2, which means they have higher concentrations of hydrogen ions. And our baking soda has a pH of 9, which means it has less of a concentration of hydrogen ions and more of a concentration of hydroxide ions. And when you mix these two substances together, you get what's called a neutralization reaction, where you're left with water. And in the case of the two reactions of vinegar and baking soda and lemon and baking soda, carbon dioxide is also released. And so because of this release of carbon dioxide, we see the bubbling that is associated with these two reactions. So that's basically how that part of the experiment works. And the role of the laundry detergent is to turn those bubbles into foam. So that's just to help see this chemical reaction in place, but it's not really a component of the chemical reaction. So that concludes today's experiment. I hope you enjoyed it, and I'll see you next time. Welcome to our day 18 experiment. Today we're going to be doing one called putting out a candle with CO2. This is also going to be sort of a twist on the classic vinegar baking soda experiment. So let's get right into it. All you need for this experiment is a candle, a cup with baking soda, another glass cup, and vinegar. The first thing you're going to do, as shown in the video, is put vinegar into the glass cup with baking soda. Then carefully lean the cup with the baking soda and vinegar into the other cup, as if you're pouring air into the other glass. Then take that glass and slowly lower it over the flame. The flame should immediately go out. So now we're going to talk about how this happens. As you might already know, vinegar and baking soda cause a chemical reaction that releases carbon dioxide. The carbon dioxide released from this reaction is enough to put out a flame because carbon dioxide is denser than oxygen, and oxygen is needed for a flame to burn. So if you put carbon dioxide over a flame, it will displace the oxygen in the area, and enough oxygen won't be available for the candle to continue to burn. So the candle would immediately be put out. Because baking soda and vinegar create carbon dioxide in one cup, when we lean it into another, that air, that carbon dioxide, is shifted into the other glass cup. So when you lower it over the flame, the carbon dioxide is released over the flame, and you know what happens next. That concludes today's experiment. I hope you enjoyed it, and I'll see you tomorrow. Welcome everyone to our day 19 experiment. Similarly to yesterday's experiment, we're going to be extinguishing a flame without blowing on it in a different way than we did with the other experiment. So let's get right into it. So to do this experiment, you need to light a candle, preferably a tea light candle. Make sure to have an adult with you when you do this for safety. And you also need 2 glasses of different sizes. So the first thing you're going to do is take the candle that you lighted up, and you're going to take a glass and put it over it. Start with the smaller one, and then observe what happens. You should observe the flame slowly getting smaller and then eventually extinguishing. Now let's try the other cup. Take note of the differences between the smaller cup and the larger cup, especially the time it takes for the flame to extinguish. You should notice that especially in the beginning, the flame is more resistant to getting smaller compared to the other one. So to understand how this experiment works, we first need to talk about how a candle burns. The reaction that occurs is called a combustion reaction. So this is basically a chemical reaction, which means that 2 things come together to form something new. So in this case, we have the wax reacting with the oxygen to create carbon dioxide and water vapor. And as a result of this reaction, we have a flame. So now, what do you think happens when we put a glass over the candle? What part of this reaction is affected? Pause the video and think about this. Well, for a chemical reaction to occur, both reactants have to be present. So if you cover the candle, the wax is still present, but the oxygen supply is limited. So the oxygen will become depleted, all of it will be used, and it'll be converted into carbon dioxide and water vapor. And so soon, the candle cannot continue to have a flame because all the oxygen is gone and the reaction cannot continue. But what about the differences that we noted between the smaller glass and the larger glass? Pause the video and think about that. If you put a larger glass, there's more oxygen available before it becomes depleted. As a result, the flame lasts longer. So that's how this experiment works. That concludes our day 18 experiment, and I hope you enjoyed it. In this experiment, we're going to add another level to the experiment we did yesterday. This one's called water rising. So let's get right into it. To do this experiment, you need a glass cup, a match and something to light it on, a candle, and a shallow dish with water and food coloring with the color of your choice. So the first thing you're going to do is take that candle and put it in the middle of your shallow dish with the water. And make sure you have an adult light the candle for you. And then after we do this, we're going to take the glass cup and cover the candle with it. And then just observe what happens. You should see that the candle extinguishes as we saw in yesterday's video, and then the water rises. So let's assume that this is what the air looks like before we light the candle, put the glass on, none of it. When we light the candle and add the jar, a few things happen. When things are heated up, molecules start to move faster and further apart from each other. So in this case, heating up the jar makes the molecules move further apart. When the glass cup is added, some of these molecules escape the jar because the heated molecules are moving further apart from each other. But then when the flame goes out, and the reasons for this are explained in yesterday's experiment, then the air starts to cool rapidly. And when this happens, then the air starts to condense together and occupy less space. And we'll talk more about this in tomorrow's experiment. But colder air is now going to shrink back together. And if you visualize that, it's going to create a sort of vacuum because we have all this air that was previously occupying the whole jar suddenly going to one area. And then that kind of causes an imbalance because we have a small area of occupied air and the outside is not in balance with that. So the outside air is going to be pushed inwards to try to equalize this imbalance. And then while these outside molecules are being pushed in, they push in the water as well. And so now we have equalized pressures inside and outside of the glass. So that's how this experiment works. That concludes this experiment, and I'll see you tomorrow. Hi everyone! In this video, we're going to do a personal favorite science experiment. The inverted balloon in a bottle. To be able to do this experiment, you're going to need a glass bottle, a balloon, some water, and a way to heat up that water. Whether it be a stove or a microwave or any other way, you can heat the water. So now, let's begin. So to begin, you're going to need to take your bottle with a little bit of water and heat it up. It's essential that the water is very, very hot, so you need to get it to at least boiling. If you're using a microwave, heat it to around a minute, but again, it depends on the microwave. And after you safely, with mittens, because the glass bottle will be very, very hot, set it down to a place where you can work. Cover it immediately with a coaster or any other way to block the hot air from escaping the bottle. And when you think it's safe, take the balloon and cover the mouth of the bottle. Adjust the balloon as necessary so that it is in the center of the mouth of the bottle so that it can easily go inside when it's ready, as you can see in the video. Then, wait and see what happens. While we watch this experiment progress, let's start explaining how this experiment works. When you heat up the water inside the glass, the water turns into water vapor, which is a gas. gases tend to move more freely and faster than liquids do. They also tend to try to move as far away from each other as possible. Then we cover the bottle with a balloon. Now the water and the gas inside the bottle starts to cool down. The water vapor that had previously been water now condenses, which means it turned back to being water. Imagine that these molecules that were all spread out inside the bottle now goes back to being a very, very small amount of the bottle. Look at how much water is in that bottle. As I mentioned before, gases try to go as far away from each other as possible. So, in a container, the gas takes whatever volume the container is in. But liquids always have a defined volume. So, when the gas condenses into the liquid, most of the molecules are going to shrink down to that very small portion of the glass. And outside, the pressure of the molecules are a lot higher than the pressure inside. Why? Well, because the pressure depends on the amount of molecules there are on a given volume. The more molecules there are, the higher the pressure will be, and the less molecules, the lower the pressure. So if the molecules are more closely compacted, there'll be a higher pressure, and if they're very spread apart, there'll be a lower pressure. So when all of the molecules come down into a very small portion, all of the liquid molecules now, there's not going to be a lot of gas molecules left inside the container. There will be some left, but there'll be a lot more spread apart, and the gas outside of the bottle will be a lot more closely compacted together. And whenever this happens in nature, well, it's going to try to reach an equilibrium so that the inside and the outside have an equal amount of pressure. And how does this happen? The air molecules outside the bottle are going to rush into the bottle to equalize the pressures. And we have the balloon in its way. So it's going to push the balloon with it in order to equalize the pressures. So if you leave your bottle out for a very long time, then when it no longer seems to change, the pressures will be equal. That's awesome, right? Hi everyone, and welcome to today's video. Today we're going to be doing a super cool experiment called the red cabbage indicator experiment. So for this experiment, you're going to need 6 glass tubes or test tubes that you can use to test the materials, and then 6 substances that you want to test for whether it's an acid or a base. Then what you're going to need is red cabbage indicator, and then if you want, you can also use an eyedropper or pipette. So how you make the red cabbage indicator is you get some red cabbage, you chop it up coarsely, and then you boil it with some water. Then you let it soak for around 15 to 20 minutes, and then once the red cabbage has completely soaked into the boiling water, then you can stop it, let it cool down, and then drain it. Then you use that liquid. That's your red cabbage indicator. Now the fun part, the testing. Pour some red cabbage indicator in each of your substances. So I will be going over what each of my substances are again later in the explanation, but let me go through them quickly. All the way on the left is baking soda, then shampoo, then water, then milk, then vinegar, then some lemon juice. So the reason why I'm doing this in this weird order is I'm starting with baking soda, which is a known base, then I'm going to lemon, which is a known acid, and then I started off before both of them with water, which is a neutral substance, which is neither an acid or a base. We will be going over this in the explanation, which you should not miss because it is the most important part of the entire video. So for this explanation, I'm going to start from the very beginning and the very basics so that people of all levels will be able to understand this experiment. So let's first get started with the basics. We need to understand the basics of chemistry in order to understand what acids and bases are and what we were testing to begin with. So the first thing that we need to talk about is the smallest unit of matter. The smallest unit of matter is our atoms. Atoms contain a few main components: a nucleus, neutrons, protons, an electron cloud, and electrons. So you can see a diagram on the right, a basic diagram that shows where everything is placed, and we're going to get a little more into what happens and what these components of an atom are. So the first thing that we're going to talk about is the nucleus. So let me get my pointer out. This over here, this red ball in the middle of the atom, is the nucleus. This is the center of the atom that contains the protons and the neutrons. Neutrons are neutral subatomic particles that have no charge. So they're a smaller component in the atom, and they're not positive, they're not negative. They're just neutral. Inside the nucleus, again, this red ball in the middle of the atom, there are also protons. Protons are also subatomic particles, but they do have a positive charge. Each proton has a positive charge of +1. Then we have another subatomic particle. These little gray balls outside are electrons. They are subatomic particles that do have a charge, a negative charge. Each electron has a -1 charge. Then the electron cloud is the purple lines that you see around here. They're not as rigid as you can see. This is a very simplified diagram, but the electron cloud is the area outside of the nucleus where electrons are moving freely. So in here I have a diagram that you can try to label, try to remember what you just learned, and then we'll pause your video, try to do that, and then we'll get into the answers. Okay, so I've labeled the labels that are in the diagram. So the first thing is that this was not labeled, but this over here, this center part, that's the nucleus. Then in the nucleus, there are neutrons and protons. The colors, I don't think they matter. There might be some sort of significance, but all you need to know for this video and for acids and bases are that that some of these are protons and some of these are neutrons. And outside of it, in these lines, so in this area outside the nucleus, this is the electron cloud. Then in the electron cloud, there are these blue balls, which are electrons. So to review, the protons have a +1 charge, and the electrons have a -1 charge. And the neutrons don't have any charge at all. All right, so now let's move on. If you didn't understand anything that I just went over, make sure you rewind the video and go over it again. Try to pause it whenever you need to process something. It's a lot, but if you really try to wrap your mind around it, it's not that difficult. So now we're going to move on to ions. So when I was trying to learn acids and bases a while ago, what really confused me were the ions portion of the whole thing. I did not completely understand where ions were, so I didn't understand the difference between acids and bases. So all of this foundational chemistry is so important to understand the difference between acids and bases. So I'm trying to make it easier for you to get it. I'm trying to simplify it down a little more, because when I tried to understand it before, it was difficult for me because I didn't really understand these basics. That's why all of this is being explained. So ions are charged particles, meaning they have a positive or they have a negative charge. This is compared to atoms. Atoms have no charge, they're balanced. The reason for this is because in atoms, the number of protons and the number of electrons are equal. So they cancel each other out. If you have 5 protons and 5 electrons, you have a -5 charge and a +5 charge, which cancel out to a charge of 0. But ions, they are charged particles. So either the protons or the electrons will be more than the other. Ions are not formed by the change of protons. They are only changed by the number of electrons. So that's super important to remember. The way you get a positive charge, well, you remove electrons. If you remove electrons, then the number of protons is obviously going to be more because you start off with an atom to begin with. So now let's look at this visually and understand this better. So on the left, I have a sodium atom. So a sodium atom has 3 rings. The inner ring, there's 2 electrons, which is always the case. In the next ring, there are 8. So in 8 atom ring is a full ring for at least the second and third shells. And then the third shell, a full ring, has 8 electrons. So all of this is a little more complicated. You would have to, if you want to truly understand each shell and how many electrons are supposed to be and the whole electron configuration, that's a whole nother video. But you don't need to know that to understand acids and bases. So for now, just understand what I'm trying to say here. So ions are always changing to have a full outer ring. That's what they want to do. So in this sodium atom, we see that there's one entire ring with just 1 electron. So this entire atom is going to be more prone to become a positively charged ion by removing that outer electron. So that's why you can see here that I wrote that the ion is Na+. What does the Na+ mean? That means that it's going to be positively charged. And how is that possible? Because in that nucleus, although you don't see it, it's going to have the same number of electrons as there are now in the atom. So if we count it, we have 11. We have 11 electrons, which means that there are also going to be 11 protons inside. If you get rid of that 1 electron in the outer shell, you're going to have 10 electrons and 11 protons, which will leave you with a +1 charge. Then now we have the fluorine atom on the other side. This is different because there are 2 electrons in the inner shell, which is the maximum in the inner shell, as I said. And then in the next shell, you have 7. So that means that you're going to have an overall 9 electrons in the electron cloud, and then in the nucleus there are also 9 protons. So since you have 7 in the outer shell and a full shell is 8, this atom is going to be more prone to becoming negative because they want to add 1 electron so that there is a full outer shell. So it'll be F-. So this is a little rundown on ions and how they work. And I hope you understood this so that we can get into learning about hydroxide and hydrogen ions, which are so essential in understanding acids and bases. So the first thing we're going to talk about is hydrogen ions. Hydrogen ions are a whole lot easier to understand than hydroxide ions because they're just like the fluorine ions and the sodium ions that we just talked about. Hydrogen atoms, which is the picture that you see there, that is not a hydrogen ion, that's a hydrogen atom. Hydrogen atoms have 1 electron on the outside and then 1 proton on the inside. So in order for this to become an ion, they are actually more prone to losing that electron rather than gaining one. Although either one results in a full shell, hydrogen ions are more prone to losing that electron. So if you lose the electron, there is going to be a +1 charge. So hydrogen ions are simply that. But hydroxide ions are a little more complicated. So this diagram is of a hydroxide ion. I know it looks a little funky, but it is a hydroxide ion. The red part of it is the oxygen ion, and oxygen ions typically have a -2 charge. Then the white part of it is a hydrogen ion, which, as we mentioned before, has an H+ charge, has a +1 charge. So what if you combine those together? What is the overall charge going to be? So I want you to think about that. If you have a -2 charge and a +1 charge, what is that going to be? What is the overall charge going to be? So pause the video, think about it. Okay, so the overall charge is going to be -1 because -2 + 1 is -1. So the whole hydroxide ion, OH, the O is the oxide part, and then the H is the hydro part, so hydroxide. The hydroxide ions are going to have an overall -1 charge. So now that we understood the basics of chemistry and we understood what we just talked about, if you didn't understand any part of it, please make sure you go back and review it and internalize everything that we just talked about so that you can understand what acids and bases are. So this is the part of the video you've all been waiting for. Let's get right into it. So acids, they contain a higher concentration of H plus ions compared to OH minus ions. So both of these components are what define between an acid and a base. What's the concentration of H plus ions? What's the concentration of OH minus ions? If you look at the little thing that I wrote over here, the H plus and the OH minus, the little greater than sign, that means that these brackets mean concentration. So the concentration of the hydrogen ions is greater than the concentration of the OH minus ions. So you'll see that acids always contain more hydrogen ions. That's so important to remember. And bases contain more hydroxide ions. So that's something that you want to memorize. Acids contain more H+, bases contain more OH-. The neutral substances, like water, contain an equal concentration of OH- and H+ ions. So now that we understand the difference between an acid and a base, let's talk about what pH and pOH means. What are those scales? I know you've probably heard of the pH scale, but pOH scale, that's a little different. So let's get into this. So the pH scale refers to the power of hydrogen, and the pOH scale refers to the power of hydroxide. So let's look at this diagram, which I really love at the bottom because it compares both pOH and pH. So if we look at this, there is this 7 in the middle where none of them are overlapping because this is the neutral portion. So water always has a pH of 7. From a pH of 8 to 14, those are basic substances. So substances that have a higher pH than 7. But they also have bases have a lower pOH than 7, if you look at it over here. So the difference between pOH and pH are basically they're complete opposites of each other. If you take the pH and pOH of any substance, they will always add up to 14. Why? Because let's say you have a substance that has a pH of 11. That same substance will have a pOH of 3. Add those together, you get 14. So they're complete opposites of each other, and the reason for that is because we know that bases always have a higher OH level than a hydrogen ion concentration, and then acids have a higher hydrogen ion concentration. So the pH scales are also at a base of 10, meaning that if you go from a pH of 7 to 8, the substance is 10 times more basic. So breaking down the whole pH scale and understanding it and the difference between pH and pOH is a whole new video and a whole new explanation. So if you guys still don't understand what the difference between pH and pOH is, please let me know in the comments and I'll make sure I do a video on that too. So for now, I think you might have at least gotten a little bit of understanding of the difference between pH and pOH, and at least you can understand what pHs are because that's mainly what we're going to be talking about, and that's mainly what's used in day-to-day lives. So if you get a pH from 0 to 6, you have an acidic substance that has a higher H+ concentration. If you get a pH of 7, that means it's neutral, and then the hydroxide and hydrogen ion levels are equal. And then if you get a substance that has a pH from 8 to 14, that's basic because it has a higher hydroxide ion concentration compared to a hydrogen ion concentration. So now let's go back to our experiment. I know we did our whole experiment, but you may not be understanding how this is connected to anything. So now let's look at what we did in the experiment and what does our data mean. So now let's talk about what the red cabbage indicator has in it that makes it change colors with acids and bases, which is super cool, by the way. So the red cabbage indicator contains something called anthocyanin. So this is a pigment that changes color when it's mixed with an acid or a base. When it's mixed with an acid, it turns red, and when it's mixed with a base, it turns green. So these are the 6 substances that I tested in this experiment. So now let's look at each of these substances, see what colors they changed, why this happened, and yeah, let's get into it. So the first thing is the baking soda. So the baking soda actually contains a pH from around 8 to 9. So this indicates that it's a base, which is correct with our observations, which turned green. Sorry about like the difference between the green and the white. The reason for this was that I added way too much baking soda, so the water was oversaturated, so it was not able to dissolve all the baking soda that I put in. But either way, just look at the green over there. You can see that it obviously changed color because of the baking soda. Which has a pH from 8 to 9. And this means that the hydroxide levels are higher than the hydrogen ion levels. For the water, we can see that the color basically is just diluted, the red cabbage indicator, meaning it didn't really change colors. And the reason for this is that the water is neutral, so the color is not going to change. It did change from normal water to this, but that's only because of the red cabbage indicator. The pigment anthocyanin did not change anything in the water. So in this case, the hydroxide concentration is equal to the hydrogen ion concentration. And now we're going to go to the lemon. The lemon has a pH of around 3, and so it's acidic. The hydrogen ion concentration is higher than the hydroxide ion concentration. So because it's an acid, it turns reddish pink. So the reason why I did these three first, I know I'm jumping around, is because baking soda is a really well-known base. So I wanted to use that as an indicator for bases, so like as a comparison. Water is neutral, which is very commonly known, and lemon is very commonly known as an acid. So one of the things that I really tested and I did not know before I started was shampoo. So what I learned about was that the pH of shampoo varies from company to company. So I can't tell you what the pH of shampoo is because it actually just depends on the shampoo that you have. So the one that I have is closer to neutral but a little more acidic. The reason I know that is because it's really similar to purple, which is the color of the red cabbage, but it's slightly pinker. So it's a little more acidic, but not completely. And this means that the hydrogen ion concentration should be higher than the hydroxide ion concentration. The next one is milk. Milk has a pH of around 6 to 7, which means that it's actually really close to being neutral. But it turned a little bit pinkish. We know it's mainly purple, as you can see, which is the color of the cabbage indicator. But it turned a little pinker than the red cabbage indicator, which suggests that it's a little acidic. So that the hydrogen ion level concentration is higher than the hydroxide concentration. So the reason why I keep mentioning the concentrations of hydrogen ions and hydroxide ions, because it's so important to remember that more hydrogen ions mean acidic and more hydroxide ions mean more basic. And the last substance is vinegar. It has a pH of around 2.5, and this is obvious because it turns reddish pink, and this indicates that it has a higher hydrogen ion concentration than hydroxide ion concentration. You can test whatever you have at home, try different things. It's so much fun to see them turn color. Before you do it, try to come up with a hypothesis about what you think would happen so that like you are mimicking a real scientific method-like approach. I hope that this was helpful for you guys and that you learned something new. I hope you understood the difference between atoms and ions and the various different chemistry topics that we discussed today. Thank you so much for joining us for our 21 Days of Science. I hope that you enjoyed these experiments and that you understood the explanations and are really advancing your knowledge of science, and while also having fun with the process. And you can find more of our experiments on our YouTube channel with the link that you can see on the screen if you are interested and want to dive deeper into it. And again, thank you so much. And I hope you'll continue to look for ways to expand your scientific knowledge and enjoy the process.